Hi, my name is Marvin, and I'm taking you on a fascinating trip into your mind. Ready? Then let's go. As software engineers, at every moment we try to make optimal decisions. And we do this to the best of our knowledge. We really try to do everything right, but we're often not aware of something that permanently stands in our way. A thing we call cognitive biases. A cognitive bias is the systematic deviation from optimal reasoning, and it can be best explained with some concrete examples. Let's have a look at testing. We tend to write more tests for our code that confirm the expected behavior than tests that might reveal failures. This is because we look for information that fulfills our own expectations. Confirmation bias is responsible for this. An error in the operation of your software leads to an accident. In hindsight, it looks as if this event could have been easily foreseen and avoided. But be aware that we usually overestimate the predictability of such events once they have occurred. We call this hindsight bias. Planning poker is on, and everyone in the room has to estimate the effort for a new feature. A colleague shows they estimate too early, and now the other team members' estimates are suspiciously close to each other. Say hello to the anchoring effect. The anchoring effect is the cognitive bias that our study is about. And it's about source code metrics that tell you how understandable the code is that you're looking at. If you use static code analysis tools or corresponding IDE plugins, you are probably familiar with such code metrics. Do you think that they can influence your personal judgment about the source code? In our study, we found that if a metric tells a developer how understandable a piece of code is, that developer will be anchored by the metric value in their own judgment of the code's understandability. If a metric tells you that a code snippet is easy to understand, it is very likely that you will stick to that metric value and rate the snippet easier to understand than if the metric had told you that the code snippet was difficult to understand. Now I want you to understand two things. First, how did we come to this result? And second, what should we do about it? Let me start by explaining our study design. 45 software engineering master students participated in our study. After a short introduction, a participant sat in front of a screen and had to do the following: understand a code snippet. The task gave the participant input values to which the output values had to be calculated according to Javadoc and actual output. After completing the comprehension task, the participant had to rate the code snippet in its comprehensibility on a scale from 0 to 10. This task was then repeated 2 more times, so that each participant had to understand and evaluate a total of 3 different code snippets. We divided the 45 participants into 2 groups. All participants had to understand and evaluate the same 3 code snippets. Everything else was identical as well, from the presentation of the code to the tasks. There was only one difference. One group was presented with a metric next to the code, indicating that the code snippet they needed to understand was relatively easy to understand, and the other group was presented with an indication that the code snippet was relatively difficult to understand. In the introduction to the study, we told the participants that this was for information only and that the metric was fairly new but had been validated. But this was absolutely not the case. We made up the understandability values of the metric to see if and how much the participants would be influenced by it in their own evaluation, and the results were impressive. On the left, we see the participants from the group who were told by the metric that all 3 code snippets were easy to understand, a 4 out of 10 on the metric scale. On the right side is the group that the metric showed an 8 out of 10 for each snippet. The y-axis shows how the participants each rated the code snippet's understandability themselves on a scale of 0 to 10. In this visualization, it is the average rating for the 3 code snippets, but the results look very similar when looking at each individual code snippet. We can see that both groups were anchored in a subjective evaluation by the metric, and that the ratings of the groups differ significantly from each other. This is a clear demonstration of the anchoring effect taking place. In our study, we also measured the actual performance of each participant in the comprehension tasks. This means that we looked at how long it took them to complete the comprehension tasks and how many of their answers were correct. The combination of time and correctness then gave us a performance score for each participant. We have just seen that the participants were anchored in a subjective evaluation by the displayed metric value. Now we have asked ourselves whether this would also lead to a kind of placebo effect and whether participants actually performed differently. At least existing literature in psychology suggests that this might be the case. If I tell you that a code snippet is easy or hard to understand, will this trick your brain and make you actually understand it better or worse? The answer is no. at least not in terms of time and correctness. Here both groups performed equally well. This in turn is of course very interesting because although they performed equally well, they rated the difficulty very differently. Now, what should we do with these results? It is good that an arbitrarily chosen metric value does not affect how well developers understand code. Given that many metrics in practice are not validated, we will probably have quite a problem otherwise. But we saw that developers are anchored in their own evaluation of code, and this could lead to, for example, a wrong prioritization of refactorings, or developers approaching code with a different mindset. We currently know nothing about the consequences of anchoring through software metrics, such as how it affects motivation and emotion, for example. What should we do right now? Validate metrics and use validated metrics. Debiasing software engineering is a valuable long-term goal, and it could already be supported by static code analysis tools relying more on scientific evidence. It's not much of an issue if a developer gets anchored in their subjective evaluation by a validated metric. Such a metric might even be able to take more factors into account and evaluate code more objectively than a developer could. But it could be a problem if developers get manipulated by a wrong metric value. And making developers aware of this might not solve the problem, since the anchoring effect is one of the most robust cognitive biases we know. What else should we take care of? In case you, as a researcher, use subjective ratings as a measure of code understanding in an experiment, make sure that individual participants are not anchored by contextual factors. Obviously, sharing code metrics could be such a factor, but so could, for example, different amounts of time available to process different code snippets. If the study cannot be controlled for certainty in this regard, I would suggest not using subjective ratings in your study. That was it, our little trip into the mind. I would like to emphasize that I had some people in my life who know just what to do. This whole study would not have been possible without the great efforts of my collaborators. If you are interested in the details of our study design and more in-depth discussions, take a look at our paper. It is available on arXiv and the link is in the video description. Finally, if you want to see more videos like this one that communicate software engineering research, then check out my YouTube channel /science. There I aim to make software engineering research more accessible to everyone who is interested in it, whether you are a scientist or a software engineer. Feel free to subscribe. Thanks for your support and see you in the next video.